Oh, I didn't see the right answer on any of those in there, by the way. So you are all in good company. So let's start with what I feel is the first part of the problem. And in in first period, I just went from one part to the next. I didn't lay out a full plan. In this class, I'm going to explain the problem a little differently. And that way I'll post the video and you can decide which part you think is the best if you want to review this. So I think there are several parts to this problem, and I'm going to show you where I think they're connected. So the first part is the ball falls a distance L under the action of gravity. That has nothing to do with the bar yet. It's just the ball making it to here, that instantaneous moment just before the collision where the ball has a downward velocity v. Right? Again, that really doesn't have much to do with the bar at all. But there's a collision now. So a collision is the instantaneous moment before contact and the instantaneous moment after. So since it is a collision, collisions are about momentum. All of them are. So I think we're going to have a section where the ball sticks to the bar and the system now has a combined angular velocity. Make sense? All right. Energy is probably lost there, especially because it's an inelastic collision. And we wouldn't use energy for that. We'd use momentum for that. Because although energy is lost there, momentum isn't. But not linear momentum, angular momentum. Because the system's going to have angular momentum afterwards. Now, there is a new part of the problem that will take place shortly thereafter. So again, I see this as a part and then this as a part. And afterwards, we're going to go from being basically perfectly horizontal, because we're talking about that instantaneous moment just after the collision. Oops. And then there's going to be the instantaneous moment just after the collision. Something like that. Where I think the angular speed is going to become greater. And that's just due to the action of gravity. So, gravity is going to pull this down and speed it up. So it has a greater angular momentum afterwards. And then we're going to be looking at how fast the ball is going at the very end. I think the ball and the bar both have gravitational potential energy that will be turned into kinetic energy. But don't forget, the bar is moving after the collision. So there's kinetic energy at the top as well. I think these are the steps that we're going to go through. And we'll highlight what I think is the math, but these are the steps. What I mean is, if I was probably writing this for a test, I would probably be kinder and not just ask for the velocity of the ball at the very end. I'd probably say something like part A, how fast is the ball going just before it hits the rod? And maybe question B, how fast is the rod and bar moving just after the collision? You see about what I'm doing there is I'm giving you the steps there. AP can do both things. They can both give you and step you through the problem. We've seen examples of that. We've also seen examples where they don't do that. You have to be ready for both. You have to be able to separate the problem into these parts. So as I look at this, I'm going to use, you could use either kinematics here, right? That's a free fall problem. Or you can use conservation of energy. I generally would use conservation of energy. It's a collision afterwards. That's going to be conservation of momentum. Right? Every collision is a conservation of momentum problem. Every one of them. So the moment one thing hits another thing, when two things are involved, it's a conservation of momentum problem. But when one thing hits something, you're conserving momentum. Now, that's not minimizing it. Conservation of momentum is hard. It's got its own stuff. Whether it's linear or angular, you got to figure out what's being involved there. But I'm just kind of giving the overall topic. And then this one clearly is going to be done by conservation of energy. Right, the bar is swinging downwards. It's not at its lowest position yet, but it's going to be at its lowest position. Now again, you're asking, or if you're asking me the question, why did you make that decision? Something falling, changing height, conservation of energy. Right? That's my big statement. That's why this one for me is conservation of energy. But we also know that it's in free fall. That's why kinematics is okay. That's why I chose that. But a change in height, and especially when you need the velocity, that to me, conservation of energy. You may not have known that you needed the velocity there, but I knew a collision was imminent. So why did I know I needed the velocity of the ball? Because collisions are about momentum, and momentum is about velocity. That's how I knew I needed this velocity here. I knew it. You may not have known that. But I knew it, and that's why I'm telling you, I knew it because a collision was imminent. So I needed to figure out what the ball was doing just before the collision, which is why I needed that velocity. Again, how do I know it's a collision? How do I know use conservation of momentum? Anytime one object hits another, it's a collision. Whether you have enough information to solve the momentum part of the collision or not, it's a collision. And collisions conserve momentum. How do I know it's angular momentum? Fixed pivot point. Fixed pivot point makes it an angular momentum collision, always. If there was no fixed pivot point, it could have been both. But there was a fixed pivot point, so it's only angular momentum. Now, that brings us to the last part. How do I know to use conservation of energy on that last part? Do you see the clear change in height? And I am asking for a velocity. Those are big, big warning signs that that's a conservation of energy problem. You're going to be setting the energy at one state equal to the energy at the other. So let's go do the solution part of this now. Ready for the math part? So the math part is cringy, but not actually particularly hard, but cringy. I mean cringy because you're going to see some weird math stuff because the numbers aren't going to be perfect. And I mean, there's numbers here. So let's talk about what I mean by that. The first part of this is pretty straightforward. The ball has gravitational potential energy here of mgl. And it's going to convert that energy into kinetic energy here of 1/2 mv squared. So I just need to set those two things equal to each other and solve for v and get the square root of 2gl. Also, you could have done v squared minus v naught squared equals 2g delta x, but delta x would be L, v naught would be 0, and you would get the same answer. I'm kind of being light on that one. We've dropped balls a lot in this class. Most all of you have a square root of 2gl in here. And no, that wasn't a ball joke, but if you want to make it one, you enjoy. So we go to the next one, because I think the next part is more of what is tough. All right, so we did our conservation of energy problem. We now have the velocity of the ball right after the collision. It's a conservation of momentum question, and more importantly, it's a conservation of angular momentum question because of the fixed pivot point. The ball gets attached to the rod, but because the rod has rotational velocity after the collision, I have to figure out the angular momentum of the ball before the collision. That's a hard one, and that one's a little harder to deal with than like linear momentum, because how do you know which one to use? It's because there's rotational velocity after the collision, and that rotational momentum had to come from the ball. That's how I know to use lowercase l, which is r times p times the sine of the angle. I need the angular momentum of the ball just before the collision, because the angular momentum of the bar just after the collision should be equal. Now, be careful here. This whole thing's happening vertically. The angular momentum of the bar is going to change due to gravity after the ball's attached. So the angular momentum only stays conserved for the instantaneous moment before the collision and the instantaneous moment after the collision. Remember, collisions are fast. So we're only talking about the split second before contact and the split second after contact. Because before that, momentum was increasing in the ball as it fell. And after that, momentum is going to be increasing in the bar as it falls. So the collision is just a very small slice of time. You guys following that? All right, so let's go ahead and work this one out. R is going to be the distance from the pivot point where the ball is just before the collision. So that's going to be 2L, because that's how long this is, right? The R is going to be 2L. P is going to be mass times velocity. Well, so that's mass of the ball times the velocity, square root of 2GL. And the angle is the angle between the velocity of the ball and the bar, but that's 90 degrees, so I'm just going to leave it out. But I'll put a little 90-degree mark there and say that this will be 90 degrees. But this is my angular momentum of the ball just before the collision. Now, to calculate the angular momentum of the bar and the ball after the collision, I will need the moment of inertia of the bar and ball together. And a bar is 1/3 ml squared, but the bar is 2L long. And the moment of inertia of the ball is just a point mass. And that's going to be m times 2L squared. Right, because it's a point mass. How do I know to treat the ball as a point mass? There's a lot of ways to know how to treat the ball as a point mass. Did I give you anything about what the ball was? No. And is the axis of rotation far outside the ball's body? Yeah. So that's why you treat it as a point mass. That's going to be 4/3 plus 4, so 16/3 ml squared. That is the moment of inertia of the system. So let's bring everything together. This is a conservation of angular momentum collision. So L has to equal L. So that's going to be 2LM times the root of 2GL equals I times omega. So 16/3 ml squared times omega. All right, well, we now need to this is algebra, this isn't physics, but I'm going to get rid of an L. I'm going to get rid of an M. And let's see, I can get rid of the 2 and make that a 4. I think that's about all. Oh, I'm sorry, an 8. But I think that's about it. So I'm just going to go ahead and resolve this. Multiply both sides by 3, and I'll get 3 root of 2GL over 8L. Now, I think this is a good point to stop and see if our units are working out, since that just looks like a bunch of letters to me. But G is in meters per second squared. L is in meters. So the stuff under the radical is meters squared per second squared. When I take the radical, it'll just be meters per second. But then I have L in the denominator, so that's in meters. So I'll cancel the meters out, and I just get per seconds. And if I don't have a unit, and I know something's rotating, what's our unit? Radians. So this is in radians per second. So I feel pretty okay going forwards. Are you guys ready to go forwards? Go ahead.
When in the collision part, you're going from the linear angular momentum, like the little L to the big L. Is it possible to do linear momentum as it hits right when it hits the rod, and then convert that combined momentum into angular?
Well, I mean, obviously the linear momentum is in the expression for angular momentum.
So that just that combines all of it.
Well, yeah, I mean, its momentum, its linear momentum is a part of its angular momentum. But remember, the angular momentum always has to be to some other point in space, which is what the R is. So if this would have, because of where it hits the bar. Remember, part of this, which we're leaving out, is that there's an angular impulse here, a torque on the bar from the ball that comes from the angular momentum of the ball. There's also a force on the ball from the bar, but we have to treat it kind of like a torque, as if the ball is rotating around the point in space. But that force on the ball slows it down. So that's happening all at the same time. Its linear motion is not separate from its angular motion. We're just counting it different because of where it is relative to the axis of rotation. Does that make sense? Okay. I mean, if we had dropped it at the pivot point, none of this would have happened, right? Because there'd be no rotation of the bar. All right. Well, no time like the present to go do the rest of the problem. I'm just going to tuck that over there because this is the initial angular velocity of the bar. But now we have a conservation ball system has. For example, there's potential energy of the ball because it is above its lowest position. Its lowest position is here. Go ahead. No, yeah, I'm going to get there. But if you want, we'll do the kinetic first. But there's a reason I want to do the kinetic last. Is that okay? All right. So that's just going to be mass of the ball times g times how high it is above its reference level, which is 2L. Now there's also potential energy for the bar. And the bar is got different potential energy because we're talking about where its center of mass goes. So that's going to be mgl because the bar's center of mass only descends to here. So that's why the value I'm using for h is different. Now, you could have found the center of mass of the system and done just one potential energy for the center of mass of the system, but you also would have had to make the mass of the system 2m. So there's lots of things you have to be considerate of there. And so I saw a few of you try to do that. Well, that's fine, but if you make it one system, you better use its whole mass. And that means also when you calculate its center of mass, you had to use the whole mass of the system, which was also 2m. So a bunch of you have center of mass on yours, but it's wrong. You probably get a point, maybe. I don't know. Test graders are like that. Let's take a look at the kinetic energy of the system. The kinetic energy of the system is going to equal 1/2 I omega squared. All right, that's how we calculate it. So we got to put I in here, which is 16/3 ml squared. And then we have to put omega squared in there, which is 3 times the square root of 2gl over 8l squared. Now, you guys look at this and get scared, but I want you to stop for a minute. Energy is energy. What I mean by that is energies get added together. These have to, in some way, be compatible so that they can be added together. So don't look at this and say, well, I'm going to leave it like that. Don't leave it like this. I bet there's some stuff here that's going to cancel out. So let's just take for a moment this and simplify it. Take a few seconds and simplify it. So I'm going to write it a second time with the square being completed. Bless you. 3 squared is 9 times 2gl. 8 squared is 64 times l squared. All right, everybody see all those things? All right, let's do, this is arithmetic, or maybe you think it's algebra. L squared and L squared cancels. This 2 and this 2 cancels. 16 and 64 can be reduced to just a 4. 3 and the 9 can reduce to a 3. All right. So let's see what I got. There's nothing in the denominator anymore except for the 4. So this is 3/4 mgl. Now, you see what I'm saying. You see why doing this is important? Because what are my other two forms of kinetic or other forms of potential energy? I have 2 mgl, 3 mgl, and now I have 3/4 mgl. I can add all that together and get one value that's in terms of mgl. So 3 plus 3/4. Common denominator of 4 and 15/4. So the total energy of the system is 15/4 mgl. And that's all going to equal the kinetic energy of the system at its lowest point, which is going to be 1/2, and then I'm going to have my 16/3 ml squared omega squared. I gotta set these things equal to each other. Solve for omega. So we'll do that next. Is that good with you guys? Okay, 15/4 mgl equals 1/2 times 16 thirds ml squared, and we want omega, so we're going to solve that for omega. Unfortunately, there's not a whole lot. I can get rid of this 2 and make that a 2. I can get rid of the m's, that's good. I can get rid of one of the l's. So those are all the things I can cancel out algebraically. I understand this is all arithmetic. The big heavy lifting was, figuring out what to do. Executing it, I know that makes you crazy, but 3 times 15 is 45, and 2 times 16 is 32, and that's going to be G over L. And that equals omega squared, so we'll take the square root of it. Yay. Sorry, not done yet. This is the angular speed of the bar rod system, but the ball is at the bottom of the rod, so now we need to find the linear speed of the ball. So I think that part's just omega times r. So we just got to multiply this by 2L. So the velocity of the ball will be 2L times the root of 45 G over 32L. I'm not quite content with that. I'm going to square the 2L and put it in the radical, because that's going to be 4L squared, and 4 and 32 will cancel down to be 8, so that'll be under the radical 45 GL over 8. So yeah, I'm going to leave it like that. G times L is going to be in meters squared per second squared. And when I take the root of that, I get meters per second. So yeah, I'm all in on that. Yeah. Is this a hard question? No. No. Is it tedious? Yeah. Now, you guys probably would do better if I had gone through and said, A, find this, B, find that, C, find this. I'm not saying you would have gotten it right, but I'm saying that if I had broken it up into tiny little problems, but what do you think your test is going to be? You got to do this. This is why is the ball falling from where it starts to striking to just before it strikes the rod. And I think we'd be best served by using conservation of energy there. Right? The ball just falls. You could just also do a motion equation if you want. There's not a lot to do there. The ball has mgl worth of gravitational potential energy, and it's going to fall to the rod. You're making the rod the reference level for that short portion of the problem. Like I said, you could also just use gravity. But if you do that part, you're going to just be doing mgl equals 1/2 mv squared, and v is going to be equal to the square root of 2gl. This is how fast the ball is going just before it strikes the rod. Any question about that part? All right. Let's move on to part 2 of this problem. In part 2 of this problem, there's the instant just before a collision and the instant just after the collision. And in the instant just after the collision, the ball and rod stick together, and that system now has momentum as a group. So, so this bar and rod together are going to begin to rotate. Something like that. So our job is to find what the angular speed of this system is directly after the collision. You have some things going for you in that we have a fixed pivot point here. Because it's a fixed pivot point, calculating the angular momentum of the ball isn't too terrible, because we know exactly where the ball strikes the rod, and we know the angle that the ball's traveling with respect to the rod. So there's angular momentum of the ball. That's the only thing moving just before the collision. And then I combined the ball and rod together as one object for the purposes of momentum. So I said there was a single object with angular momentum after the collision. Any question about that? A lot of papers didn't have this that I looked at, but a bunch did. You will need the moment of inertia of the ball rod system. So I did the rod 1/3 m 2L squared. I tried to tell you guys the rod is 2L long, so when calculating its moment of inertia, you had to use 2L for the moment of inertia of the rod. So if you see that circled on your paper when you put just L there, that's why. But I did give you that hint, or at least it wasn't even a hint. I tried to tell you explicitly that it was a rod that was 2L long. But I do have to add the ball as a point mass. A bunch of you tried to put in something like 2/3 or 2/5 mr squared. Did I tell you the size of the ball in any way, shape, or form? No, and it's rotating about an axis well outside of its body. So you treat the ball as a point mass, and that's m times 2L squared. And I don't mean this to be disrespectful. You have to be able to interpret that on the test. They're not going to come out and say it's a point mass. You have to know that if the axis of rotation of an object is well outside the body, and if they don't give you anything about the shape of the object, it's a point mass. I believe this comes out to be 16/3 ml squared. All right, so we'll need that. Now, that being the moment of inertia of our system, I did r times p times the sine of the angle from the momentum of the ball just before the collision, and I set that equal to 16/3 ml squared omega. This is to find out what the angular speed of the rod-ball system would be just after the collision. Any question about that? Now, if you're trying to take notes, you're trying to figure out why I'm doing some of the things I'm doing, and you don't really know the choices I made, we have a collision. Collision's always going to be a momentum problem, always. And the reason we can't use linear momentum here is because there's a fixed pivot point in the system after the collision. So I have to treat it as an angular momentum problem. This is just going to be 2L, because that's where the ball strikes the rod, times m, the mass of the ball, times its velocity, the square root of 2GL, times the sine of 90. Nothing special about that. You could, I guess, square the L and put it in the radical, but that doesn't really save you anything because we got L's on the other side. So 16/3 ml squared times omega. There's nothing pretty about this, but it's just the way it's got to be. So I'm going to multiply the 3/16 on both sides. I'm going to cancel that. I'm going to cancel one of the L's, and I'm going to get, I believe, 3/8 square root of 2GL over L equals omega. I'm going to stop here. I mean, is my arithmetic, is my algebra okay? This is a good place to check, because this is the first time where I'm getting something that's just a collection of letters, and I'm trying to figure out, am I on the right track? Check your units. Everything in here, meters per second squared times meters is meters squared per second squared, but it's under the radical, so that's meters per second. And then I'm going to divide by meters, which leaves me with nothings per second. Now, what is my likely unit if I'm in nothings per second? All right. Does that make sense for this to be equal to omega? Seems like it is. So now I can go on to the next phase of the question, because this problem is just that punishing. So over here, I now have this rod thingy, which I've kind of exaggerated, the fact that it's that's moved a little bit. It's still really horizontal. It's just acquired an angular speed. Is that okay with you guys? Because the truth is, it's about to swing downward. So I need to deal with energy here. I decided not to find the center of mass of the bar rod system and just treat the potential energy of the bar and rod separately. So the ball, the ball and rod, the ball is going to descend a distance 2L. So it has gravitational potential energy for the ball of mg times 2L. The bar, well, it's going to have gravitational potential energy as well, but that's going to be based on its center of mass falling just a distance L. So its gravitational potential energy will just be mgl. But here's the part that's going to be just a mess. The kinetic energy of the bar is, well, 1/2 times the moment of inertia of the bar, which is 16 thirds ml squared, times its angular speed squared. So that's 3/8 square root of 2gl over L quantity squared. Well, that's pretty yucky. Not going to lie. That's hideous. The only good news is that that's just going to equal 1/2 I omega squared on the other side, because the whole bar has no potential energy at the bottom. It's just swinging, so it has kinetic energy. But I got to add these three things together. I believe there's some simplification to do in here. So let's do some simplification. A little bit of algebra. So I've got a 3. Well, I can't do that yet. Let's go ahead and square. I think if I square it, I can at least remove the radical. So 1/2 16 thirds ml squared 9/64 2gl over L squared. No, all I'm doing is trying to simplify this because there's lots of numbers and things here. So I can do the 3 with the 9. That gives me a 3 there. I can do 16 and 64 because 4 times 16 is 64. I got a 2 and a 2, so I can get rid of those. And I've got an L squared and an L squared. I think that's all I can cancel out. So what does that leave me with? An M, a 3/4, a G, and an L. So it looks like that whole thing is 3/4 mgl. That's how much kinetic energy it has. How convenient. Aren't the other two forms of potential energy just some multiple of mgl? In fact, I think if I just add all this up right now, I'll have 2 plus 1 plus 3/4. So let's see. 3 is 12/4. And 12 plus 3 will be 15/4 mgl. That's how much energy the system has just after the collision. And I have to set this equal to 1/2 16 thirds ml squared times omega squared. All right, now we're getting somewhere. We're not done yet. I didn't ask how fast the bar rod system was rotating. What did I ask? I asked how fast the ball was moving, and the ball's at the bottom. So I decided not to sub in V over 2L here. I decided to just go ahead and find omega and then multiply that by 2L when I was done. So that's what I'm going to do. So let's go ahead and do a little algebra here. Cancel the M's, cancel one of the L's, cancel the 2 and the 16 to get an 8. I think that's all the canceling I can do. So multiply both sides by 3 and I get 45. Divide both sides by 8 and I'll have 32. And then I'll have G over L equals omega squared. Does this make any sense? No. Yeah. Because it's nothings per second squared. I'm about to take the square root of that, so that'll be nothings per second. That's velocity. So the square root of this, 45 over 32 GL, equals omega. So if I want to find V is going to be R times omega, which is 2L times 45 over 32 G over L to the 1/2 power. That's all in the radical. You could put 4L squared inside there if you wanted, and that would simplify at least the L's, or maybe just drop the L inside there, because that'll just move this L from the denominator to the numerator. So that's kind of how I express the answer. On my paper, I did that. 45 30 seconds GL. That's how fast the ball's going.